In this video, we will describe a method for solving a linear inhomogeneous differential equation. So a linear inhomogeneous ODE, a method that is somewhat different from the standard three methods that are usually considered in a sophomore level ODE course, namely undetermined coefficients, the so-called key identity evaluations, and the third method is variation of parameters. Those are the standard three methods that you encounter in this course. For simplicity, we shall restrict ourselves to second-order equations. So we will only consider second-order equations. What we say will apply to higher-order equations, but we'll make life easy on ourselves. And the method we're going to describe is the so-called green function method. Well, in analogy with all of the methods that we have developed for solving ODEs, the green function method involves evaluating antiderivatives. So you can't get away from that. You're doing integrations whenever you're solving differential equations. And therefore, the practicality of the method depends on our ability, in particular cases, to actually carry out anti-differentiations. Okay, we'll consider the constant coefficient case first, and then we'll make a comment on the variable coefficient case later. So let's consider a second-order linear constant coefficient inhomogeneous equation. So an equation of the form ay double prime plus by prime plus cy equals f of t. The assumptions are that a, b, and c are constants, and the given function f is continuous on some interval. We know what the general solution of such a gadget looks like. It's of the form alpha y1 plus beta y2 plus, let's write y sub capital P of t, where alpha and beta are arbitrary constants. y1 and y2 are linearly independent solutions of the homogeneous equation, that is the equation where f is 0, that is the equation ay double prime plus by prime plus cy equals 0. And of course y sub p, the p is for particular, is a particular solution, some one solution of the inhomogeneous. From the theory you've learned, you know how to find the linearly independent solutions of the homogeneous equation, y1 and y2. Those come from the roots of the characteristic polynomial of the differential equation. The whole point is how, when we're dealing with an inhomogeneous equation, do we produce this yp? How do we find yp? Now, the green method requires that the second-order equation be in normalized form. So we will divide out by the leading coefficient a, which we can always do because a can't be 0. If a were 0, then we wouldn't have a second-order equation. So we will write our equation in the form y double prime plus a1y prime plus a2y equals f of t. So it's now in normalized form. Then the green function associated with this, the function g of t, is, by definition, the unique function which satisfies the homogeneous equation y double prime plus a1y prime plus a2y equals 0, and the initial conditions, y of 0 equals 0, y prime of 0 equals 1. That's the green function. Which we usually say is associated to the differential operator d squared plus a1d plus a2 d to the 0, where d is d dt. D to the 0 could also be written as the identity or left out entirely as the notes do. Then, the solution, the particular solution to the differential equation can be obtained in some sense miraculously by integrating from 0 to t the green function at t minus s against the inhomogeneous term f of s ds. The miracle is that function is a solution to the inhomogeneous equation. In fact, it's exactly the one which satisfies the initial data yp of 0 equal yp prime of 0 equals 0. That function is the unique solution to the inhomogeneous equation satisfying these two pieces of initial data. Now that is not at all obvious, and we want to show why that is the case. And in order to do so, we need to borrow a result from multivariable calculus. And so here's the result that we will borrow or make use of. If you have the integral from 0 to t of a function of two variables, t and s, integrated with respect to s, and you differentiate that with respect to t, the result you get is comprised of two terms, the first of which is just obtained by differentiating under the integral sign, and the second term is k at tt. So we want to show why that is the case. Here's a proof of the fact. So we're going to compute the derivative with respect to t of the function. I used g again. Probably should have used a different letter, but g of t is the integral from 0 to t of a function k of ts with respect to s. So how do we compute the derivative? We evaluate g at t plus delta t, subtract g at t, and divide by delta t. And we need to see what happens to that quotient as delta t tends to 0. So if we put it in, there is the difference quotient. Right? Here's the value at t plus delta t, the value at t. Subtract them, divide by delta t. Now I break this integral up into two integrals, one from 0 to t and another from t to t plus delta t. The second guy goes from 0 to t already, so I can write these two terms as the sum of these three. So I now have my two terms, and now the assertion is this term. It's sort of obvious. The only place we have delta t's is here. The s is the same. And so this is purely the definition as delta t tends to 0 of the derivative of k with respect to the first variable t. So that's what it says here. The first term is obvious. And the second term is really obvious as well. It follows from the fact that if h is a continuous function, then the limit as delta t tends to 0 of this expression is, of course, just h of t. It's basically just the fundamental theorem of calculus. So if you apply that here, then the result as delta t tends to 0 is just what you get by putting s equal t, and that's where the ktt comes from. So let's go back and use this fact in the computation that we were working on. All right, now we will use this fact from multivariable calculus applied to this purported particular solution of our inhomogeneous equation. We know how now to differentiate this function. Yp prime is obtained by first differentiating under the integral sign. So that gives us g prime t minus s f of s ds, plus the term obtained by evaluating at t and s equal t as well. So if we put s equal t, we get g of 0 f of t. But recall g was selected to be a solution of the homogeneous equation in which g of 0 is 0. So this term drops out. Now let's differentiate it again. Yp second derivative. Since it's again given by an integral of the form to which the multivariable calculus fact applies, we can again differentiate first by differentiating under the integral sign. So we get the second derivative at t minus s, f of s ds, plus that integrand at tt. So this time we get g prime at 0 f of t. But recall g prime, g was selected so that g prime of 0 is equal to 1. So we just get that expression. Now the claim is that yp is a miraculous function which satisfies three properties. Its initial data, that is yp at 0, is 0. That is obvious because when t is 0, I'm integrating from 0 to 0. And it's also the case for yp prime at 0. Because again, it's just the integral from 0 to 0. There's nothing else, and so that gives me 0. The last assertion is that this function actually solves the inhomogeneous equation. Let's see why that's the case. Yp double prime plus a1 yp prime plus a2 yp. You see very quickly it's going to have this term f of t plus an integral from 0 to t. There will be an f of s common, and then the three terms give me as follows: g double prime t minus s, that's from here, plus a1 g prime of t minus s, that's from here, plus g of t minus s, or the s. And the fact is, of course, that the expression in the square brackets is 0. That's because g is a solution of the homogeneous equation. And so all that's left is f of t. And I've thereby proved that y sub p is, in fact, a particular solution of the inhomogeneous equation, the one which actually satisfies these initials. So indeed, this function given by an integral is indeed a solution of the inhomogeneous equation. In fact, the unique one satisfying these initial data. Two comments. First, our ability to make good use of this technique depends to a great extent on how well we can anti-differentiate that function. We'll see in a moment that sometimes we can, sometimes we can't. The other comment is that in the notes, there is an arbitrary initial data point used instead of 0. In that case, one just changes 0 to the initial data point. Everything else remains the same. So now let's look at two examples, one of which we can do the integral and the other of which we will not be able to do the integral. Here's our first example. Y double prime plus y equals tangent of t. Notice that undetermined coefficients does not apply because the tangent function is not one of our candidate types for that method. And so we're going to use the green function method. And in order to do so, we have to write down the unique function g, which satisfies the homogeneous equation, and y of 0 equals 0, y prime of 0 equals 1. And it doesn't take you long to figure out that the unique function that does that is the sine of t. Okay, therefore by the green function method, our particular solution of this equation is given by integrating from 0 to t the green function evaluated at t minus s times the inhomogeneous term tangent s ds. Now that's not a difficult integral to express because you can use the sum formula for the sine function to write it as a sum of two terms. Let's do that. We'll expand sine of t minus s, and so we get sine of t times the integral cosine s tangent s ds, and the second term, a minus sign, we'll get cosine t times the integral from 0 to t sine s tangent s ds. The first integral is very easy to do since tangent is sine over cosine, and we just wind up with sine t times the integral of the sine function, and if you do the integral you get 1 minus cosine t here. And now for the second one, the obvious thing to do is the following. Since tan is sine over cosine, you get sine squared over cosine, so you replace the sine squared by 1 minus cosine squared. Cosine s, and so you wind up integrating the cosine and the secant, both of which you know how to do from calculus. And if you do that, you wind up with two terms, cosine t, sine t with a plus sign, and the other term is minus cosine t times the log of secant t plus tangent t, that being the antiderivative of the secant function. So there's some cancellation, and you just wind up with sine t minus cosine t times the log of secant t plus tangent t. That's the unique function which solves the inhomogeneous equation and whose initial data is 0. And if you look, you see that that's a perfectly good function between the interval of minus pi over 2 and pi over 2. So that's a nice example in which the method of green function gives us a totally explicit solution because we're able to do the anti-differentiation. And now for our second example, y double prime minus 2y prime plus y equals e to the minus t squared. Nice inhomogeneous equation. We need, again, it doesn't lend itself to undetermined coefficients, so we want to try a green function. In order to get our green function, we need the solution of the homogeneous equation with the appropriate initial data. It's clear that the characteristic polynomial here is r squared minus 2r plus 1, which is r minus 1 squared. And so our linearly independent solutions are e to the t and t to the t. And a little bit of work gets you that the green function is just t e to the t. That's the solution of the homogeneous equation, which satisfies that g of 0 equals 0 and g prime of 0 equals 1. And therefore our solution, our particular solution, is obtained via the green method by integrating from 0 to t the green function at t minus s, so t minus s e to the t minus s times our inhomogeneous term e to the minus s squared ds. Now that's a nasty integral, not one that you can evaluate in terms of elementary functions, but in fact one in which you can evaluate in terms of a rather well-known special function known as the error function, usually denoted ERF, or ERF of t, which by definition is 2 over the square root of pi, a normalizing factor, integral from 0 to t e to the minus s squared ds. It's not surprising that that error function arises because of that e to the minus s squared. Not so amenable to work by hand. Let's turn MATLAB loose on this problem. Here's the MATLAB evaluation. S and t are symbolic variables, and I'm integrating exactly what I wrote down on the previous screen, t minus s, e to the t minus s, times e to the minus s squared. The variable in integration is s, and I integrate from 0 to t. And I suppress the answer because it spews across the right side of the screen. I then printed it up, and let's see what we get. It evaluates it immediately. I need to bring up the MATLAB screen, and there's the answer. in terms of the e to the minus t squared, and there's our error function. It occurs here and again here. Pretty complicated, but nevertheless, in terms of that special function, we can actually find the solution to the inhomogeneous problem. So we solved this problem. We found a solution to this inhomogeneous equation by the green function method in terms of antiderivatives involving the error function. Final comment, in fact, it's more, this method of the green function is more or less equivalent to the method of variation of parameters. And in fact, that is shown in the notes when the green function method is extended to variable coefficients. I'll let you look that up on your own.